We'll give it 1 or 2 more minutes just to make sure we see some people coming in here. So let's just give it a minute to make sure everyone comes in. As people come in, just note that this is recording. And we'll start in just about a minute. We're on the line, we're all ready, but we know people do trickle in always a minute or 2 afterwards. So. Okay, I think it's time to get started now. Enough people are here. I'm sure people will be joining as they come in. So welcome, everyone. My name is Steve Razy. I'm the head of the Department of Physics at the University of Windsor, and we're very pleased that you're joining us here today for the second of talk in our virtual seminar series for undergraduate physics students. We will be posting these on YouTube about a week or so, a couple days at least after the talk is held. So if you'd like to go back and revisit them, we would encourage that. If you're in the audience with us now and you found this talk very interesting and you'd like to share it with the other students, just point them to the YouTube and they'll be able to watch it as soon as it gets posted, and we would greatly appreciate that. That would be fantastic. So without further ado, our speaker for this week is Professor Chitra Rangan. So Chitra is, for the people in the audience who may be students, she is an expert in what's called AMO physics, atomic molecular optical physics, and has over the course of her career run a very long series of extremely interesting theoretical experiments investigating the nature of such interesting things as quantum mechanics and the interactions of electromagnetic radiation with ultra small particles, and studying the quantum dynamics of these systems. And the range of projects that she's worked on over the course of her career has been extremely fascinating. And today she's going to talk about something really interesting, which is, can ultrafast laser pulses make water magnetic? And we're really looking forward to what that title may mean. This is going to be an excellent talk. There will be definitely time for questions at the end. If you have something you want to put in the chat, that will be fine, but we will definitely take questions at the end. You'll be able to unmute yourself and ask a question, or post your question in the chat and one of us will read it out for you as well. So we look forward to that discussion at the end of this talk. Professor Rangan will talk for probably about anywhere from 50 to 60 minutes, and then we will have time for questions at the end. So we thank you all very much for joining us, and I will turn the floor, or the screen as it is, over to Professor Rangan. Thank you, Professor Rangan.
Thank you very much, Dr. Razy, for the kind introduction. So I'm hoping that everyone can hear me and see the video, see my screen as well. Can someone just say yes?
Yep.
Okay, awesome. Thank you.
Perfect, perfect.
Okay, so as advertised, the title of my talk is Can Ultrafast Laser Pulses Make Water Magnetic? Well, I guess a better way of stating that, a more scientific way of stating the same title, would be the modeling of ultrafast pulse scattering by molecular clusters. And most of this work was done by my former PhD student, Chris DeLoretto, who is now an assistant professor at Northwest Missouri State University. Okay, so if you look at the last 10 years, there have been a huge range of very high profile articles in many important journals. And what they all say is that they describe a series of experiments. And in this experiments, they have ultra-fast light pulses that scatter off a liquid, a dielectric liquid such as water. And they claim that they're able to make the material magnetic and produce what they claim is called optical magnetism. So this is a very dramatic claim because, you basically have, if you think about it, you have a, some water. If you take water in a glass and you shine ultra fast light on it, how do you make that magnetic? So we decided to investigate this claim. And if you look at the experiments, this is the earliest of them. They all have, they're very similar. So they basically have a cuvette or a little glass container containing some dielectric liquids such as water, carbon tetrachloride, benzene. And then they shine they send in a very fast pulse of light coming in this way. The light is polarized in this vertical direction, and that comes in. This light illuminates this cuvette. And then, as always, you know that if you send in light through a medium, three things can happen. You get absorption, you get transmission, you get absorption, and you get scattering, right? So you have some light that is transmitted, some light that's absorbed, and then the light that is scattered. Now, light is actually scattered all around. But what they look at is the transverse scattering. So they look at scattering from the at the 90-degree perpendicular direction. And what they found is they put a polarizer on this end of the experiment, and they were able to rotate the polarizer. So if now you have light coming in that's polarized in the vertical direction, it's scattered. When it's scattered, they thought that most of the light should be polarized again in the vertical direction. But they also found that there was some light being polarized in the horizontal direction. So they called the vertical direction polarization, they gave it the label sub ED, and the horizontal direction was called sub MD. And I'll tell you why they chose those in a second. Okay, so this is the experiment. What did they find? They found that in the orthogonal direction, there was a significantly scattered light intensity. And they were able to find that this ratio of the intensity of the, so they nearly found about a quarter of the light was scattered in the horizontal direction. Now, if you remember your E&M, if you have an electric dipole that's in this direction, the light that comes out in the shape of a donut, but the polarization is also in the same direction as the electric dipole. Whereas if you have a magnetic dipole, so you have a loop, current loop, so the dipole is pointing this way, and it also produces a donut. And if you look at the polarization of the light, it's in this direction. It's in the orthogonal direction. So they basically said, oh, we see light in this orthogonal direction. This must be a magnetic dipole, and therefore they called it optical magnetism. And they see the same thing in lots of materials, like water, carbon tetrachloride, benzene, etc. Now, these explanations for these experiments are very problematic because what you have is that in order for their experiments to match up with their claim of optical magnetism, they have to have a magnetic permeability, effective magnetic permeability that has to be multiplied by this very large number C. C is 3 times 10 to the 8 meter per second, as you all know. So if you want to get them to agree with their experiments, you need this artificially large mu effective. Well, most materials in the optical region of the spectrum are non-magnetic, right? So mu naught, mu equals mu naught. And the second issue is, so their claim was, you have this light that comes in, but it sets all these electrons in the material spinning. And when the light goes up and down, so this electron spin this way, and that produces a magnet or a magnetic dipole radiation. Well, the measurements that they make are actually well after the pulse has left the medium. So there should not be any more of the spinning going on. So that doesn't make sense either. It also doesn't say why water is a polar molecule. Carbon tetrachloride is a highly centrosymmetric molecule because it has no dipole moment, it has no quadrupolar moment. The lowest moment it has is an octopole moment. Benzene is a planar molecule. So why do all of them behave the same way? Because they will all not torque the same way. So these experiments don't make any sense. So now I have to say that, when we talk about optical magnetism, it's not that actually there is no optical magnetism. There is a completely um, uh, legitimate field called artificial magnetism that of research, right? So in the optical spectral range, most magnetic materials don't have a good magnetic response, but you can have a dielectric response is very strong. So your dielectric permittivity, which is epsilon, can be positive, negative, or zero. And what you can do is you can engineer displacement currents and conduction currents, which so act like sources for artificial magnetism when these specially designed materials called metamaterials are illuminated with electromagnetic fields. So an example of this is something that was found in 2012, where you actually have to engineer these materials. These are not naturally occurring materials. You have to engineer these materials so that when light acts on them, you can create currents, and that produces magnetism. It still does not produce magnetic radiation because, as you all know, if you want to produce the magnetic dipole radiation, it's not enough to have a magnetic dipole. You have to have an oscillating magnetic dipole. So the magnetic dipole, the current direction has to switch back and forth as well. So these are all some issues with their interpretation of the experiments. So what we're saying is that we agree with the experiments, but we think the experiments have a much simpler and elegant explanation, a theoretical explanation. So our theory is that if you have, in our version of the theory, we say, okay, let's model this liquid with an ensemble, and we'll, because everything is easier if you take it as a sphere, we'll assume that this ensemble is a spherical ensemble. And it has about 4,000 dipole emitters or atoms. And we place them in the density of approximate density of water. And we apply this ultrafast pulse that comes in, but the pulse is near resonant with this dipole. Now, if you have an atom, this atom can absorb radiation and it can re-emit the radiation as well, right? But the atom can also spontaneously emit from the excited state. So when this atom emits from the excited state, this re-emitted radiation will next excite a neighbor. And this happens in 3 dimensions. So you have an atom that gets excited, it gives out radiation as it emits radiation, and then the emission will be excited by will excite the next atom, and so on. So each atom actually does this. And now supposing I have an atom that is excited in this direction. When it emits radiation, it's going to emit in this dipole pattern. And if I have an atom here, it will get excited because there is a polarization in this direction. But if there is an atom here, that does not get excited because there is no field. So this atom gets excited, but this item will get excited in a different direction because the polarization is in a different direction. So this quantum dipole orientation is going to change over time. And so for the ensemble as a whole, these interactions between particles of emission and re-emission or scattering produce these electric fields that are going to be orthogonal to the initial field. Now we can calculate this, and we calculate the free currents, which tells us how much electromagnetic field is produced, and we can monitor those. So in order to do this, the problem to sort of solve this problem, what we need is to calculate how a dense ensemble of quantum emitters that are driven by an electromagnetic field, what is the dynamics of these? So this means that what we have to do is we have to solve two equations. One is we have to solve Maxwell's equations for the light that propagates through this medium. And we have to solve what's known as Lindblad equations, and I'll tell you about that in a minute, to solve how the atoms themselves go up and down, behave in this electromagnetic field. But remember, we're actually solving 4,000 atoms. Each atom is a two-level system, so each atom has two energy levels, but we have 4,000 of them. And the number density is about 10 to the 27 per meter cubed, which means you have, that's about the density of water. And each two-level system is illuminated by this local field, and it has a spontaneous emission rate. So essentially what we're doing is we're looking at something like a mean field where the spontaneous emission from each atom contributes to the local field, and then the atom at that position is going to be excited by the incident field that's coming in, plus the local field that is due to the interparticle interactions. Okay, so if we want to do this calculation and we want to do this exactly, it becomes very expensive. The best scaling that you can have is it scales as n to the 4, where n is the number of energy levels. And so if you have 4,000 atoms and 2 energy levels per each atoms, you see the scaling is not very good. So what we do is we do something called a mean field calculation, which makes the scaling lower. Now, there are two approximations that many people in the community have used, and we kind of test out to make sure that this is actually, these are good approximations. The first approximation that people tend to use is that they say that two-dimensional simulation. So if instead of taking a cluster in 3D, you can just take a small circle, a 2D simulation. And they say, well, it will give you the same answers as 3Ds. We're actually showing you, we will show you that this does not work. And the second thing they say that is a current wisdom in the field, if you will, is that if you just take a short pulse of light and see how the system behaves, then in the long term, you don't really have to evolve over a long time. Even in the long term, it's actually going to give you very similar answers. So evolving for a short time is enough. And so we will show that both of these approximations are not sufficient, and we have to actually do better than that. So just to remind you, how do we look at atoms? So for you may have seen in your quantum mechanics classes that to describe the state of an atom, we have to use a wave function, and we use the Schrodinger equation to describe how the wave function evolves. Well, that is good. That is true only as long as the atom is isolated, and your states are always stationary. But when you have an atom interacting with the environment, then the atom can actually spontaneously emit from the excited state to the ground state. It can decay from the excited state to the ground state. That cannot be described by a Schrodinger equation. It actually has to be described by, and it cannot be described by a wave function either. It has to be described by a density matrix. So if I take a single atom, single two-level system, and that can decay from the excited state, and I drive it with a resonant laser pulse, then the population actually eventually comes to a steady state at some point. But what also happens is that the phase relationship between the ground state and the excited state will start to degrade over time, and that's called decoherence. And so this is basically what you see here. The coherence of the system basically starts going down and decaying. So the effect of having any two-level atom interact with an environment is that the coherence of the system, or the phase relationship between the different eigenstates, will start to decay. Okay, so just let's put a pin in that, and I'll come back to that in a second, in a bit of time. So if we want to say that, okay, we want to model the system, but here if you have two energy levels and you have a laser pulse that actually couples these two, and I assume that the laser pulse is polarized in the y direction, and then so that basically takes these two levels, and so in that axis of quantization, these two energy levels are shown here. However, because I'm actually going to get I'm going to get electric fields that are pointing not only in the y direction, but also in the other z and x direction. Even though I have only two energy fields, energy levels, I cannot have just two energy basis states. I have to have four basis states. I need to have one ground state, and then one excited state when a y polarized light comes and excites it. I need to have one excited state when the x polarized light comes and excites this atom, and I need to have another excited state for when the z polarized light comes and excites this atom. So this is, instead of having a two-level atom, even though I have only two energy levels, I need four basis states to describe this system. So normally we only have one direction of light, and so that two levels is enough. But when you have multi-directions of polarization, you need to have multiple basis states, multi-dimensional basis states. So then I told you about the density matrix. The density matrix is formally written like this. So some of you may know this already, but I think there's fewer of people probably have learned about the density matrix at the undergraduate level. And the equation of motion for a density matrix is shown here. So I just want to show you that this is very similar to this is equivalent to the Schrodinger equation, the time-dependent Schrodinger equation for a wave function that of an atom which is isolated from the environment. So if an atom is isolated from the environment, you would use the wave function and you would use the time-dependent Schrodinger equation. When the atom is not isolated from the environment, then you use the density matrix and the density matrix equation. And you can also show how the spontaneous emission affects this evolution using this Lindblad superoperator. Okay, so once you do that, we can also figure out what is the free current densities due to these due to the motion of these charges. What is the current densities, and plug that as a source into Maxwell's equation. So remember, I told you I want to actually solve a couple of Maxwell's equations with the Lindblad equation. So this is all the mechanics of that. And so essentially what you have is a quantum state of the system determines the response to the fields, and then it also generates the fields, and we put that in the Maxwell's equations, and then the light propagates through the medium. Okay, so this is just graphically what we do. We just say, well, these are the initial conditions. Then we propagate the Maxwell's equations, and then say how the material responds to this, put it into the quantum model of the density matrix, and then that contributes back to the Maxwell's equations, and we go in a loop. So we use a self-consistent mean field algorithm that we extended to 3D. Now, if you want to know about the mathematical details of how we do this, these equations are, you can see here that you have a curl, so that's a spatial derivative. And here you have a time derivative. So you have to actually be using both the spatial derivative and the time derivative. You have to solve both. And so you can do that using you solve the spatial derivatives using Fourier transforms, and then the time derivatives using the pseudospectral time domain method. And this makes the problem much easier in computationally. Okay, so let's talk about the first results that we got. Before I go to the results, if there's any questions that people would like to ask, this would be a good point to stop and ask now. Okay, hearing none. Okay, so the first calculation was the following. So we basically just took a cluster of 4,000 atoms, and we chose the energy spacing between the ground state and the excited state to be that of this neodymium atom. and assumed the number density to be about 4 times 10 to the 27 meter cubed. And we monitored what is the light that's scattered in the transverse direction at this point P. What we saw was something really interesting. So when we saw we are using a 10 nanometer nanosphere, and we're looking 3 nanometers outside it. The electric field is about 1.5 times 10 to the 9 volts per meter. And the time we look at is about 10 to the about 200 femtoseconds. So 200 femtoseconds into this problem, we actually see that there is some extra spectral lines that appear. So we were all excited about this because we said, oh, you know what, maybe we're getting new spectral features due to this. And that could be really useful. We could use it in applications and so on. Didn't turn out that way, because if you wait long enough, these are actually transient solutions, and so they go away. So that was a little bit disappointing, but also interesting. Why does this happen? So you have shifted frequencies that show up under monochromatic or single frequency excitation for short time scales, but they vanish rapidly. And the question is why? So what we decided to look at is we decided to look at two things. Okay, we started looking at the current, the free current densities that we calculated, and at the top. So let me just explain this graph to you. So at the top, this is the free currents in the same direction as the initial polarization of the light that comes in. And in the bottom, we have the free currents in the orthogonal direction to the light that came in between. Okay, so and these are at different times. So initially, what we see is the free current is in the same direction throughout the cluster as the initial polarization. So this is almost as if you have a conductor who's basically saying go up and down, and all the atoms are basically going up and down together. But after a bit of time, what you see is you get currents in the orthogonal direction, and there seems to be a decoherence that appears. Okay, and so that's as if you have this incoming light that's telling, let go up and down, and then they all start going up and down, but at some point they start going in the orthogonal direction. Okay, and you can see that here as well. So initially there's almost no current in the orthogonal direction, but as you get later in time, you're actually seeing current in the orthogonal direction as well. So that is an important observation. So next, what we can do is, remember I told you we have 4,000 atoms. We can calculate, and each atom has 4 energy levels, 4 basis states, 2 energy levels, 4 basis states. And we can actually take the ensemble average of all of these atoms, atomic states. So we can get sort of an ensemble state of all these atoms. And what we see is that if I look at the population as an ensemble, so I'm going to look at this as an ensemble. So remember, each atom has 4 states: the ground state, then the excited state in the initial polarization, and then 2 excited states in the orthogonal polarization, right? So if I look at the excited states in the initial polarization, they are heavily populated, and then they start dying down. The states in the orthogonal polarization initially have no population, but they start building up, like so. Okay, so this is as an ensemble. The other thing that happens is, supposing I look at how coherent the phase relationship between the ground states and the excited states. For each individual atom that's in this green, and I apologize for not changing green and red. So the ones has a larger amplitude is the green one. These are the coherences of the individual atoms. whereas the red line, or the line with a smaller amplitude, is the coherences of the ensemble. So what this is saying is that even though the individual atoms are all coherent, as an ensemble, the coherence has gone down. Okay, so that's an interesting result, right? So individually, they're all still coherent, but as an ensemble, they're not coherent as much anymore. So what we're actually seeing is that we're seeing this rapid onset of disorder in the free currents. And the states that are not driven by the initial field population, for field polarization, are being populated. And these are caused by these interatomic interactions that I mentioned at the beginning of the talk. So now we can actually try to do this, try to say, okay, can we make a simpler model for this? So supposing I said, let's take this ensemble picture. And this ensemble picture, I'm going to make it into, I'm going to say, let's assume that I'm only looking at the ground state and the excited state in the initial orthogonal direction as a two-level atom. Then what this looks like is as if the population in the excited state is going down, and the population in this two-level atom itself is leaking out. So I can basically model that by this. This is just a very simple model. So I have a two-level atom with an excited state decaying down, and I'm also losing population elsewhere. So what now I have is an ensemble decoherence rate and a rate of leakage. So I have an ensemble decoherence rate of 3.56 times 10 to the 13 hertz, and a state leakage rate of 1.85 times 10 to the 13 hertz. Now, okay, so this is a number, right? But why is this interesting? It's because if I look at the single atom spontaneous emission, single atom spontaneous emission rate is 2.95 times 10 to the 6 hertz. This is 10 to the 6, this is 10 to the 13, right? So what this is saying is that collectively as an ensemble, the ensemble decoherence is 1,000,000 times more than the decoherence of an individual atom. So just by this interaction between particles, the decoherence of the ensemble is actually 1,000,000 times more. Okay, so that itself is a very interesting result. Okay, so just to give you another comparison, if the spontaneous emission rate of the single atom is 344 nanoseconds, the ensemble decoheres over 28 femtoseconds. That's a really small number. So the consequences of this, as far as of a theoretician is concerned, is two of them. Okay, Dr. Razy has a question. Right, so did we see the spectrum of the input radiation before we saw shifted output radiation? And I said monochromatic. That's correct. I did say monochromatic, meaning single. So that initial calculation I showed you was for a single frequency pulse, and we didn't model the frequency spread of the pulse yet. So we're going to do that next. But even for a single frequency pulse, we're saying that this is important to actually propagate it for a long time. Okay. Okay, thanks. Okay, so as far as this calculation sets up a theoretical limitation for two very popular computational techniques. So one of the things that many people do is that when they take clusters of atoms, they basically just take two-level atoms with only one directional basis set. And when you do that, that means that you're not really taking into account the excitation in perpendicular directions. So that cannot be right. The second thing is that using this short pulse method to describe all types of frequencies, excitations, that limits the, it's a limited calculation, because the onset of disorder at short times is basically telling you that you can get all these different spectral features. And very often that people who use these kind of computation techniques overestimate the quantum optical effects of these calculations. Okay, so here is a calculation that shows what is the dependence of these on the number density. So this, if I change the number density as the atoms get closer, so this is as the atoms get closer together, you see that the decoherence rate, the ensemble decoherence rate increases. This sort of makes sense. As it gets closer together, then it's easier for the atoms to excite in the orthogonal directions, and that's basically what you see by the state leakage rate as well. Now, if I plot these, what I get is this particular curve. Okay, and this is for two different values of the intensity or the incident electric field. And so if I plot this particular curve and this particular function that fits this curve is very well known in biophysics. And this it basically tells you that there is a competition between two effects that's going on. And here the competition is that you have an incident field that's actually trying to drive this transition up and down, and you have the interparticle interactions that is trying to populate the other states. And so the competition between these two effects is dependent on the intensity of the field itself. And it determines when the number density at which this disorder rate starts to saturate. And so you can actually write down these functions like so. Okay, so the key takeaway point here is that the disorder rate of depends on the intensity of the electromagnetic field that is exciting it. Okay, so Chris was giving his progress report in his committee, and so this is my student who did Chris DeLoretto. And one of the things that people said was, this is so complicated. Is there an easier model to think about this? And so he said, yeah, so I'm going to come up with this model. And so basically, Chris's model is that let's take the state of the system and you describe it by a single 4x4 matrix. Okay, so remember what I was doing before is that I have 4,000 atoms. Each of them is described by a 4x4 matrix. So I have this huge system that describes the entire ensemble. But Chris wants to describe the entire ensemble by a single 4x4 density matrix. And so we have, similar to what we had before, a single 4-level system. But here's the thing. We have to describe the interparticle interactions. So we have to describe not only the emission from the excited state to the ground state, but we also have to say, okay, if an atom absorbs from along the y direction, from the y polarized light, and then emits into the z direction, how do I show that? And so we showed that using dephasing rates. So essentially, if I have an atom that emits from the x excited state, and then that gets reabsorbed by a neighboring atom into the y excited state, then that is described by a dephasing, going from the x to the y. So this is a model that's inspired by the Foster resonance energy transfer, again in biophysics. So we can do that as well. So we can include all these dephasing rates. And so we end up with a model that does not describe a single atom, but it describes an ensemble. So in a single atom, all these red lines would not exist. But in an ensemble, we claim that all these red lines will describe the ensemble states accurately. And so then the Hamiltonian is simple. It's just a 4x4 Hamiltonian, and we can solve the equation of using the density matrix equation. And so then the answer is simple. Now, why is that such a huge advantage? Because the full calculation using 4,000 atoms and 4 levels per atom used to take us about 10 CPU days on SharkNet, which is the supercomputing system that we use. This system, you can just run it on your laptop, before you know it, it actually solves the problem, right? So it's a really awesome, it's a really quick method for modeling an entire ensemble. And the nice part is if you compare the full calculation with the single particle model, the answers are not terribly different. They're actually pretty good, right? So this is at a particular density, and then we'll show you at a different density. So this is actually a very fast and easy way of actually doing calculations, just to give us an idea if we are in the correct ballpark. Now let's go back to the initial problem that we talked about. The initial problem was that we have a water, we have a cuvette of water. There is a light that comes in, ultrafast pulse of light. I believe this is 20 femtoseconds. And then we look at the light that's scattered in the orthogonal direction and see if you can find what is the ratio between the light that's scattered in the orthogonal direction with orthogonal polarization to the incident polarization. And here what we see is if we did the calculation using both the single particle model as well as a full model, the calculated value of this ratio is 0.3. And remember what it was with the experimental value. It was between 0.25 and 0.3. So this model actually explains the experiments pretty well. Similarly, if I look at how this, for a 100 femtosecond pulse, how does this ratio change with intensity? This is very similar to what is seen in the experiments. So here is a calculation where you vary the intensity in one direction, the number density in another direction, and calculate this ratio. And we see that again, it's very similar to what was observed in the experiments. So we believe that our model explains the experiments really well. So to answer the question, can the ultrafast pulses make the water magnetic? Well, we don't believe so. We believe that the results of the ultrafast scattering experiments can be explained by including these interparticle interactions and in this theory of scattering of ultrafast laser pulses from a molecular cluster. Now, these results actually are very interesting because it allows us to study many other problems. So one of these are a few of the problems that we are currently working on. One is to look at if we can take a cluster of 3-level atoms. Remember, we took a cluster of 2-level atoms. If we can take a cluster of 3-level atoms and then study how a different process such as stirrup might work, that would be very interesting in this. Another area of research is to study high harmonic generation from clusters, because clusters are very interesting because locally they have a density of a solid, but globally they have a density of a gas. So it's sort of in between the two regions of high harmonic generation gases and high harmonic generation from solids that many people are working on. Actually, you can listen to a talk in the same series in January from my colleague, Dr. Hammond. And then you have one other thing we would like to study is optimal control of emitted radiation from clusters. So how can we actually make this cluster not spontaneously emit, or maybe increase its spontaneous emission? Can we shape the spectrum that is being emitted that's being scattered in various directions? So those are the kind of things that I'd like to study. I just want to put in an advertisement that if there are, for the students in the audience, that I do have graduate positions available for the fall 2021. And so if you're interested, please contact me. And my email's down here. Okay, so to conclude, I think we've shown that interatomic interactions cause large decoherence in coherently driven ensembles of atoms or molecules. And we have the single particle method that produces a very quick and accurate estimate of the dynamics of a large quantum cluster. this theory basically explains a lot of the features of the experiment, such as the intensity dependence. Why do you need strong pulses to see the effect? You don't see the effect in weak pulses. And it also shows you, it also tells us why you can actually see this in a variety of molecules, like a polar molecule like water, centrosymmetric molecule like carbon tetrachloride, planar molecule like benzene. It provides this elegant alternative, we think, to optical magnetism theory. And so I'm happy to answer questions, and also if anyone wants to contact me to discuss more, I'm happy to do that as well. I just want to finish by thanking the people who fund this research, NSERC, of course, for the Discovery Grant funding, SharkNet, and the University of Windsor. Thanks for your attention too. And feel free to just put up your hand or ask me questions. Thank you.
Great, everybody. That's fantastic. Let's give, we're still trying to figure out how we do virtual clapping online, but people, we don't have a virtual clap thing. So sometimes, I don't know, people share their screen and they do this. I don't know. We don't have a clapping icon. That was fantastic. We already have some questions coming in the chat. So Dr. Rangan, I guess you can see them, so I don't need to read them. So
yeah, so Dr. Drake asks, what are the limits on the single particle method? Does it always work? It does not always work, of course. I mean, there are several limitations. One of the thing is, one thing we've assumed that it's just that the light emitted from one atom will excite the nearest neighbor atom. We have not actually looked at atoms in the next nearest neighbor and so on. And we also have not, it is essentially a simple model, right? Because we are basically assuming that the entire ensemble is doing one thing. So it works better when it doesn't work so well when the atoms are sort of in the intermediate region. So if the atoms are very far apart, then it works because it acts like a single atom. If the atoms are pretty close together, then it works. But in the intermediate region of density, it doesn't work as well.
Yeah, so it's basically a nearest neighbor interaction model. Is that one way to put it?
It is a nearest neighbor interaction model.
Yeah, okay.
That's correct.
we've got a question, Chitra, from Shima M, if has got her hand up. So please, please feel free. Go ahead. You're welcome to unmute yourself and ask Dr. Rangan, or, oh, here comes Chitra. It's coming in the chat there. Thank you.
Yeah, I already sent my question. Sorry.
Yeah. Oh. So does the single particle method only work to describe what happens to ensembles in static measurement? Dime resolved high harmonics or pump probe measurement? Actually, the answer to that, Shima, is that I don't know. Because I think, so the single particle method works better after the incident pulse is done. So after the incident pulse leaves the ensemble, then then it's a time dependent calculation, and it actually works there. I'm not sure it can actually do time resolved high harmonic generation, but I think it can represent pump probe measurement after the pulse has left the system.
Thank you.
Okay.
Well, I've got a question then, Chitra.
Sure. Go ahead.
I believe you answered at least part of it, which is as a non-theoretical person, I was intrigued by the 4,000 number, and I did assume that that was limited by computational power or something like that. So two questions, which is, one is that, would that still be true if you were doing it the older brute force kind of way? And two, if you can only do 4,000, how good was that assumption, considering they're putting it into a whole cuvette?
Oh, okay. Yeah.
So I'm not having done those calculations. I'm not clear how close to reality that actually is.
Right.
If you take
So,
my meaning.
Yeah, I understand what you're saying. So essentially the way we arrived at 4,000 was we actually started with smaller clusters and just started building bigger and bigger clusters.
Okay.
And at some point it just stopped changing the answers.
Oh, okay. Oh.
So we said, okay, 4,000 we can handle. That's the number we're going to keep.
Oh, okay. Oh, interesting.
So, but then, yeah, it does take a long time.
Sure. Okay. All right.
Is that Dr. Corkum? That's pretty cool. Hi.
Professor Corkum is here.
I will ask you directly.
Okay.
Chitra, have you thought about air lasing? Air lasing is a case where you've got free induction decay, giving you radiation generally on a gain medium going forward, but there's all kinds of complexity in it. And it seems like a place where your model might have some relevance in the sense that you have many, many different, like similar air molecules that are lasing. And I wondered if you thought about it at all.
I have not thought about it, but I
Okay.
did read actually something. I read a thesis by Metagarda's PhD student
Okay.
who has done a similar calculation to what you
Okay.
suggest using free
Okay.
induction decay. And I was just talking to my former student, Chris, and we were looking at that and saying, okay, this looks very similar to what we are looking at.
That's what I thought. As I listened to you, I thought it was very
Yeah.
close.
So yeah, I will definitely look at that. Thank you.
Okay.
So I want to particularly invite questions from undergraduate students, and don't feel, like you can't ask a question, because only when you ask you can learn, and I can learn too.
No such thing as a stupid question.
That's right. Yeah, sometimes actually the undergraduate students are the ones who ask the most interesting questions, because they don't have prior knowledge. And so they,
Right.
the question they ask is like, oh yeah, why did I think about that? So feel free. I think, yeah, I know for a fact there's at least one. Zach's here, so Zach's my undergrad. Oh wow, now I'm looking at the participants.
Was there a reason you were looking at neodymium atoms, Chitra? I was kind of surprised by that. I was like, ND,
Yeah.
I was trying to figure out what that meant when you said it said ND, and then you said neodymium. I'm like, oh, I was not thinking that of all the things that ND could be. I mean, I know neodymium very well, but that was not what I thought you were going to say.
Yeah. So actually, I did have a few things that I cut out from the talk because it was I wanted to have time for questions. And the reason for this choosing neodymium was there was an experiment that was done using. So I was working on something else at that time, and so this was actually trying to the issue is the following. So if you have if you have solar cells, right? The band gap of silicon is about 1 electron volt, but any wavelength, so any frequency that's lower than 1 electron volt in the solar spectrum is essentially wasted, because you can't produce carriers. And so one of the proposals that was done that people were doing experimentally was to put clusters of neodymium atoms on top of a silicon substrate, and their idea was that this neodymium atom would be able to enhance the electric field around this cluster and then produce increase the efficiency of solar cells.
Right.
But one of the other things also that was predicted, but we thought that we should test it, was that this this cluster of neodymium atoms would also generate extra spectral lines. So essentially will up convert light And so then that would allow it to increase the efficiency. So you get more light in a frequency greater than 1 electron volt. And so that's what we were trying to test. And we found that, well, that's only a transient solution, not a steady state solution. So that's the history behind the neodymium choice.
Okay. That makes a lot of sense.
Yeah, but all the latter calculations were done for water.
Sure.
And for carbon tetrachloride as well.
Sure.
I want to say hi to Andre as well.
It's good to have Paul Corkum on the line.
Yeah, and Andre and
So we're extending our reach.
So we're very interested in magnetism. So you have a number of people who are thinking about magnetic materials. So the title pulled us in. But this is very similar. This idea is very similar to the air lasing ideas.
Yeah, but you know,
that's why I asked you if you thought about applying it or thinking about air lasing at all and what the implications were in air lasing.
But I think you know, one of the things, I think I sent you an email about this, Paul, was that some of these ideas that you had on you know, producing these circular currents.
Yes. Yeah.
That could be something that's related to artificial magnetism.
Yes. Well, Shima, one of the people that asked you a question, was is starting to work in that area. And so you have a number of people from Ottawa and pulled in by magnetic fields.
Okay.
I think, or at least partially.
Okay, I think if there's no other questions, then we can probably stop the recording then, I guess, Chitra. And I'd say we should all thank Chitra one more time and